Hello and welcome to 2-2 higher degree polynomial functions. Our first example asks us to sketch some transformations of functions. So in A, graph y equals negative x plus 5. Okay, a negative x plus 5, negative x squared, x to the fifth, I'm sorry, is going to end up looking somewhat like that. An x plus 1 to the fourth is going to end up looking somewhat like that. This is just a general sketch. Okay, just a general sketch. One thing we're going to learn about today is the leading coefficient test. Basically what this says is you can determine your end behavior of your function or of your graph based on the leading coefficient of the highest term. So it's all based on this idea. If your highest exponent is odd, and so such as x to the third, x to the fifth, so on and so forth, then and your leading coefficient is positive, then the graph falls to the left and rises to the right. However, if the leading coefficient is negative, it flips. So as x goes to the positive infinity, it goes down, and as x goes to negative infinity, it goes up. When it's even, both of them go up or both of them go down. So when you have an odd function, when you have an odd powered function like x to the third, x to the fifth, it either goes up left, down right, or down left, up right. And when it's an even one, it either goes up up or down down. I will zoom in, pause it as you need to write this down. So applying the leading coefficient test, basically describe when they say right-handed and left-hand behavior, we're saying what is the end behavior of each graph. Well, for A, it's negative x to the third plus 4x. Because it's negative x to the third, it's an odd powered function, which means as x goes to negative infinity, meaning it goes to the left, it goes up. And it goes to the right, or x goes to positive infinity, it goes down. On B, I have a positive x to the fourth, which means n is even, which means left and right are both up. And here I have a positive x to the fifth, so the left behavior will go down and the right behavior goes up. If a polynomial function, if an f a function is a polynomial function and a is a real number, then the following statements are true. That if you deduce it to x equals something, that is a zero of the function or a root. It is a solution of the equation. X minus that number is a factor, and that number, comma 0, is an x-intercept. Think of it as when you had a quadratic and you had to reverse FOIL it to get x minus this times x plus this. They're saying those are factors, and what the x equals, if you set it equal to 0 and solve for x, then that is a 0 of the function and a solution. Okay, copy that down. So finding the real zeros. Determine the number of turning points in the graph of the function. Okay, so when I take this, negative 2x to the fourth plus 2x squared, it factors, I can factor out a negative 2. We'll just factor out a positive 2 for now. A positive 2x squared times negative x squared plus 1. All right, remember this is 2 times x plus 0 squared. And then I'll have negative x squared plus 1. To solve for the next one, I can just set all of these equal to 0. X plus 0 equals 0, and negative x squared plus 1 equals 0. This factor is x equals 0, and this one I get negative x squared equals negative 1, x squared equals 1, x equals plus or minus the square root of 1, which is 1 and negative 1. So each of these are a factor of the equation. They are a real zero of the equation, which means each of them is a turning point. So there are 3 turning points. All right, so once again, when you factor an equation, you find its real zeros and go from there. Each of those becomes a solution and a turning point. A repeated zero is when you have the same value more than once. So up here in this problem, I had 2 of them that were at x equals 0. There were 2 of them at x equals 0. So it has a multiplicity of 2. So anytime I have more than one, it leads to a multiplicity of k, depending on how many that it's repeated. If you have an odd multiplicity, it crosses the graph at that point. And if it is even, if you have an even multiplicity, then the graph touches the x-axis, but it doesn't cross the x-axis. We call that the bounce. So if I only have one or some other odd number of factors for that specific number, it'll cross it. But if I have 2, 4, 6, or 8, or etc. of the same factor, it bounces. Da bounce. So sketch the graph of this equation. If I were to factor it, I would immediately come in and factor out an x cubed, and then I would have 3x minus 4. Set them equal to 0, I have x cubed equals 0, or x equals 0, 0, and 0. Here I would have 3x minus 4 equals 0, 3x equals 4, and so x equals 4/3. Now my end behavior, because I have an x to the 4th and it's positive, is going to go up and up. When I look at my problem and I have 0, I obviously have an x-intercept at 0 and a y-intercept at 0. So I know it's going to cross there, and then at, that's 1, we'll call that 2, so we'll call that 1 1/3. So I know my graph is going to hit in this area right here at 4/3. So I know it's going to go up there, I know it's going to go down there, and I know it's going to do some wiggly, it may do a bounce, it may do a curve, something down underneath. So that's an approximate sketch of the graph. You can check it against graphing calculator to get a more precise one. So all I did is find the zeros, plot them, find the end behavior, and plot that too. And then connect the dots. Sketch the graph of this polynomial. Well, I get x times negative 2x squared plus 6x minus 9 over 2. Okay? So when I sketch this graph, I have x being 0. X equals 0. It will cross 0 at some point. To find the rest of it, I'm going to use good old Mr. Quadratic equation. So x equals the opposite of b, negative 6, plus or minus the square root of 6 squared minus 4 times a, which is negative 2, times negative 9 over 2. All over 2 times negative 2. Simplifying this on the inside, I get 36 minus, I'm going to put all this in parentheses, 36 minus 4, the 2's cancel out, 4 times 9 is 36, so I get 36 and then all over negative 4. So x equals negative 6 plus or minus 0 over negative 4. So x equals negative 6 over 4. Because this is a squared, what that tells me is that x plus 6 over 4 squared. So x will be 0, my multiplicity of 1, and x equals negative 6 over 4, and that's a multiplicity of 2. So I know that it's a negative x to the third, which means it follows this function. So what it's going to do, when I sketch my graph, negative 6 over 4 is negative 1 point, it's negative 3 over 2, which is negative 1.5. Negative 1, negative 1.5. So my graph is going to come down like this and bounce, and then cross 0 and go down. Okay? So when I have a multiplicity of 2, it bounces. When I have a multiplicity of 1, it crosses. It had a multiplicity of 2 at negative 3 over 2, which means it bounces at that point. The graph comes down, hits it, bounces, and then think of the x-axis as like a wall with doors. At the multiplicity of 2, because it was even, it hit the wall and it bounced off, but at x equals 0, that was a door and it went right through. And that was today's lesson.